This mechanism knowledge is done his PhD in Delft University with the accounting, and his direct supervisor was Usageand, which you certainly know now. Then he went to Sydney, was working on and now the recent 2 years he got postdoc group leader position in Forschungszentrum Mourik, working in Aachen, and is now here to tell us about nuclear spins or spin qubits and his research. Thank you.
All right, good afternoon everyone. It's a pleasure to be here. I haven't seen much of the city yet, I only arrived last night, but it looks like a very nice, interesting city to have a summer school in. So, you can find more about quick advertisement of my lab, our lab. You can find more about it on our website, but we are a junior team in Jülich, on the way now for about 2.5 years. Experimental research, focusing on the one hand spin qubits, on the other hand super semi devices towards Josephson junctions, superconducting qubits, perhaps based on hybrid Josephson junctions. So that's sort of the broad topics that we cover. For this summer school, what I have in mind, I asked around a little bit, and I don't think there has been a basic introduction to spin qubits yet in the summer school. So this first lecture, I want to cover that. This is basically, it should be very easy going, but it's meant as an introduction from an experimental perspective, what a spin qubit is and how we operate it typically in these semiconducting devices. I think that will occupy today's slot. Then tomorrow morning, but we need it sort of as a pretext to get to understand how the devices work in which we can operate single nuclear spins. Okay, that is the thing, the message or the topic I really wanted to cover here, and we need to know how spin qubit devices work. So I think that will be tomorrow morning, and yeah, I suspect that most of the slot will be about the details of the operation of these nuclear spins and the physics of it. And then hopefully on Thursday we can look at some perspectives what you can actually do with these systems. It's a bit of a rough schedule. You can imagine that here maybe some stuff spills over into that slot or the other way around, depending how fast we go. Okay? Now, tomorrow afternoon I give an additional lecture, but I really hope it's not a lecture but more a discussion. So I will guide it with a deck of slides and a presentation. But the topic I want to discuss is sort of the next part in the sequel of what Sergei Frolov showed you before from the experimental perspective. Now I want to talk more about the hype aspect of it and how that can generate potentially unreliable scientific papers and what that means for our community or what we can do to improve on our practices, etc. Of course, I don't know all the truths either, right? Like maybe I don't know any truths there, so I need it more really as a discussion where I sort of set the stage. That's for tomorrow afternoon. I think it's the last talk of the day, so yeah, I think scientific content-wise it won't be very technical or so, more meant to discuss about our practices. Having said all that, I think let's start, and this is derived from a block of lectures in the master's course at RWTH Aachen. That's been taught for many years now by Thomas Schepers, an experimentalist, experimental professor in Munich and Aachen. And I started co-teaching this course with him last year, and I think this is a good deck of slides yeah, to talk about spin qubits. Any questions, interrupt and ask, etc. There's no point. This is supposed to be fairly basic, so I hope that you all can follow and understand. And otherwise interrupt. So to start, David is actually one of my current bosses until he retires later this year. Yeah, I'm sure that if you work with qubits, you have heard of the Vincent criteria. It is basically, you know, an essay-style paper where he lists a number of criteria that any working quantum computer should obey. It's fairly generic, it's not very mathematical. yeah, you need a well-defined qubit. You need to make many of them, like many of these qubits need to be fabricated, etc. You need to be able to initialize such a qubit. Then it needs to stay coherent on a time scale that's much longer than it takes you to operate on the qubit. Of course, you need to be able to define those operations, so not only initialization, but also changing the state in a controlled manner, and readout. In practice, I would say that readout and initialization is almost the same thing in many instances. So, yeah. I think from today's perspective, this is a very easy to understand and comprehend and logical, sort of set of criteria that we need. But back in the late 90s, I think this was quite eye-opening to many people to see this spelled out. And the point of the presentation today is basically to go through how a spin qubit works and sort of see how we meet all the time one of these criteria. I won't make it explicit, but it should be quite clear, I think, throughout. All right? So, spin qubits. It all starts, I would say, I will follow sort of the history of the field a little bit, and that means we need to start talking about semiconductor heterostructures. Because spin qubits really originate from material science in the 60s, 70s, 80s, etc. And then in the 90s, this was perfected to the point you could make spin qubits from it in the early 2000s. So if we look at the periodic table, we're going to look for semiconducting materials where we can use the typical framework of gates, dielectrics, etc. to make gate-defined electrically controllable devices. So you look at the periodic table, what are the most attractive candidates for that? Of course, we have the group 4 elements, silicon and germanium. Very well known, of course, in the semiconducting industry. Also very attractive candidate systems for silicon for spin qubits. Nowadays, these are the leading materials and alloys of it. Back in the days, it was actually not at all this platform where spin qubits were developed. Instead, it was from compounds and mixtures even of that, namely aluminium, gallium arsenide, and gallium arsenide. So 3-5s. 3-5s also have been historically a very important platform for spin qubits. Nowadays, I would say it's slowly phasing out. I can already tell you the reasons. It's nuclear spins in the material that you cannot get rid of. I will talk a little bit more about it later on. Yeah?
What is the criteria for the elements to be a platform for the...
I will hopefully answer it in a few slides, but mostly practical constraints. Is the material available? Can you grow it? And then can you fabricate electric devices on top of it that allow you to control the density in the material?
Okay, so there's no criteria for the intrinsic properties?
No, not really, no. By now, for example, we know that you don't want a material that has nuclear spins that you cannot get rid of. But that is like, it's not a truly fundamental criteria. Like, it limits your performance at some stage, but it's totally possible to work in a material with nuclear spins. So this is not a fully comprehensive list. I am expecting that graphene in 1 or 2 years there will be a spin qubit in graphene. I don't know, like it's not so scalable graphene, so it may not be the most useful, but we will get it. There have been spin qubits in carbon nanotubes. Any semiconductor you can shape into an electronic device. You can control the density of in principle, suffices. But we need confinement. That is a key criterion, right? Like we need to be able to confine electrons or holes to the point that we can work with single electrons or holes. That is, I would say, the most important aspect of it. So if all this is how the field started with all these various combinations, and people started working in at interfaces of 2 of these semiconductors. And I think the famous one that we all know about probably is aluminium, gallium arsenide, gallium arsenide. So what happens here is that you have a large band gap, a small band gap, you put the 2 together, there is a band bending happening upwards, and at this interface here you create a little potential well, and here you can have electrons. So by growing this on a wafer scale, you actually get a 2-dimensional plane of electrons. Okay? And this can be, this is underneath the surface, near the surface, so whatever, like 50, 20, 50, 100 nanometers below the surface or so. So you can put an electrostatic gate on top to control the density. This material system has been extremely important in condensed matter physics. It was developed in the 1980s to the point where you could make nice quantum transport devices out of it, and I would say many major discoveries have been made based on this material platform. New discoveries in quantum Hall effect, quantum point contacts, etc. But also the first spin qubits were made in this material platform. Took another 15 years almost, early 2000s, that people could make spin qubits in this material. So many of the results I will show throughout the talk are based on this material platform. There is one of the major tweaks that people had to do was put a remote dopant layer, and yeah, that's sort of like a lot of material optimization and investigations went on here. And this resulted in the end that if you look at the bulk of gallium arsenide versus this is called a two-dimensional electron gas because it's in a two-dimensional plane, you can see that as this material was optimized and improved, people were able to get very high mobilities. So mobility basically means here that these electrons behave fairly ballistic. Mean free paths are of the order of micrometers, and that is important because now you enter the lithographic skills that were getting more and more accessible in the late 80s, 90s. Okay? So this is now two-dimensional. So we have basically gone from 3 dimensions to 2 dimensions, but we need to end up with a 0-dimensional object, a fully confined electron. Yeah?
Sorry, why high mobility is important when I'm doing a qubit? Because when I'm doing a qubit, the electron should rest.
So what we need is to be able to have a well-defined, phase-coherent standing wave within our confinement potential. That is what you need from the material, and that you get through getting a high mobility. Basically, low mobility means that your electron is scattering all the time, that it's hard to get a properly confined standing wave within your confinement potential. This was a major problem with silicon for a long time. It was basically too disordered, too low mobility. So from an experimental viewpoint, usually we say that mobility, we equate it in our minds with very disordered, low mobility, high mobility. Not so disordered, you can have phase-coherent physics going on there. So this was why this mobility had to be pushed to the level of at least 10 to the 5 or so before people could start confining electrons to the point you can see quantum effects. Yeah. It's a big material problem, I would say. A lot of, we're looking here at decades of materials research. Very impressive what material growers actually have achieved. So that is done. This material, aluminium gallium arsenide is made in MBE systems, molecular beam epitaxy. I'm no expert on that. I'm a device physicist, so I don't know all the ins and outs myself either, but you can see these are very complex chambers with many several sources. You have analysis tools on there, often heating or cooling depending on the type of material. This needs to be ultra high vacuum, and this takes typically years of optimization for a lab to get it to the point where they can produce high quality materials. And that is in our community how we often operate. There is an institute or a group that can make the perfect material for our purposes, and then teams like my own, people like myself, collaborate with the growers to make electronic devices out of that. So we ask them for material, sometimes we give input how exactly they should grow the layer stack, etc. And yeah. All right. There is, and I will talk about it at the end, there is of course by now alternatives to the point that gallium arsenide has been phased out. I would say mostly for spin qubit research, still some things are being tried there, but by now it's mostly overtaken by silicon-based materials that can either be bulk silicon with dopants in it, and you use the single dopant as a spin qubit. It can be really transistor-like objects, so metal oxide semiconductor type structures on top of the silicon, and you work at the silicon-silicon oxide interface. Or, and it's probably the leading contender at the moment, it is having another heterostructure where you use an alloy of silicon germanium, and in between it you have this very strained silicon quantum well. So you start from a regular silicon substrate, you have a buffer layer, and you end with a, in this case it's quite deep, you have a thin 10, 50 nanometer thick silicon layer that is now strained because there's germanium mixed in the silicon above and below it. The lattice constant is slightly changed, and the silicon here is now strained, and that is a way to crank up the mobility a lot actually, and also remove degeneracies in the band structure. I will come to that at the end. The counterpart has been popular for the last 4 or 5 years or so. That is using germanium. So instead of high concentration of silicon, you have now a high concentration of germanium. You use a pure strained germanium quantum well. That is a whole conductor, so we work in the valence band here. Yeah, I would say the experimental progress in the last 5 years is quite impressive, and that is the media platform we work on in my own team. All right? This just as a pretext. The main working horse structure or device that we need to talk about and consider is the quantum dot in a semiconductor. So the way this works is we already, through material growth and by working at interfaces, etc., we manage to confine our electrons from 3D to 2D and basically engineer their properties to the point that they become more suitable for this type of research. But that's not enough. We want full confinement, where we have really created a particle in the box-like state where only a single electron or a countable number of electrons can be present. So the way this works is that you put a dielectric on top of your heterostructure or a cap material that allows you to put a metal on top here that can act like an electrostatic gate. So we can apply now a voltage here, and it's isolated, insulated, so we get a potential, an electrostatic potential that actually allows us to shape the two-dimensional electron gas. And here the game is to get the shape and the dimensions right, so small enough and in the right dimensions that we can basically completely have a little puddle here of electrons that we can completely change the number of electrons of. So go down to the very last electron, have a countable number of electrons in there. And this is the very first generations of devices, I would say from the early 2000s, where people were trying this. You can see this is 1 micrometer, so this is a few hundred nanometer big gates, which is in today's standards quite big. But this was how people started off. In this case, they worked through depletion, meaning that through the design of the material, the two-dimensional electron gas is already present at 0 gate voltage, and instead you need to push it away where you put the gates. So you can see that all the area here where there is no gate, you can have electrons, and underneath the gold gates here there are no electrons. So this is, here you are putting a negative voltage on all these gates to push electrons away, and this is your confinement. Right? And this is another example from Japan, from NTT. Similar idea. Also in the depletion mode. Okay. Now, what have we generated here? And that is I would say, a surprisingly effective, almost classical model, and it is looking at the charging energy of a tiny capacitor. And for many of the work we do in spin-to-bit land, this is pretty much the only model you need to work with the small corrections for quantum effects. So, the structure schematically we have a source and a drain, to talk in transistor language, so we have charge reservoirs here, and in the middle we have a small puddle. That of course is an island with a small metallic-like island with a capacitance. Now, the capacitance of this island, we can calculate that, and it comes with an energy, and that is what we call the charging energy. Okay? So, very basic derivation, and we end up with the charge on the island squared divided over the capacitance. And the point is that when you make this island very small, the capacitance gets very small as well, and because it's in the denominator, the charging energy gets large. And it turns out that you, with the lithographic techniques that are available, you end up with an energy scale that is visible in the laboratory. And this is all classical, of course. The other important aspect to understand is that this leads to a discretization already in the available energy states of this island. This is all classical, there's no quantum in here. And the reason is that every time you put an extra electron on this small island, you need to pay this charging energy, and once this is more as the thermal energy of your system, you will have only a discrete range of energy states available for your island. So in terms of chemical potential, which is the typical thing we work with in the laboratory, because chemical potential is, we can adjust the voltage difference across the device. What this means is that the various different states, this is basic math, taking these capacitors in the circuit into account, we can define an arbitrary number n of states, and then the difference between two of these states is what is the chemical potential of the island, or the dot. And then you get, again, this expression in there that contains the charging energy. So what this means is that we have a ladder of possible chemical potential states now of the island. And every time this sits in between the source and drain chemical potential, we can have transport through the device, but when there is no level in between, we are blocked. So from a device operational perspective, this is something you can observe. Okay? So, if you now look at the difference in chemical potential between two of these states, you will find that there is the charging energy in there. Okay? So it all is about making the island small enough compared to the effective temperature of your system so that this quantity becomes observable. And that is why you need the lithography to be of good enough quality and your system to be cold enough so that you can observe this. And that has been achieved for the first time in metallic islands, I would say in the late 80s, early 90s, people have seen this effect for the first time. Metallic islands, and now this had to be translated to semiconductors, and that took basically another 10, 15 years for people to develop that. Alright, I already mentioned that. Now in terms of transport through this structure, we can observe single electron tunneling now. So we have a position like this, where there is no available state on the island chemical potentials in between the bias you apply, the bias window you apply to the structure. So then we don't have any current. Then there is a level in between those two chemical potentials, the source and the drain. We can actually have current, and we observe a current peak. And then if you pull this ladder up or down, again, you are blocked again. This, of course, we can control with the gate. If you saw in all these formulas here, there is the gate voltage via the capacitance that we have. So the gate voltage is in there. So we have continuous control over the ladder of chemical potentials on the dot, and every time we are on resonance with, or we are in between the chemical potential difference between source and drain, we can have transport. So this is gate controlled. So on this axis here, we have gate voltage. We get peaks in the conductance, the current of the structure, and every time we go over a peak, we know we have added the next electron to the island. On a metallic island, this is an arbitrary number n. It is of the order of hundreds of or thousands of electrons. But in the semiconductor, because of the much lower density and the longer Fermi wavelength, we can actually go to the last few electrons. This is how this looks in an experiment. So this was done on some semiconductor material. I think this may have been on the nanowire, I'm not sure. You can see that here we are in the band gap of the material, and here you see that every time we add an electron to the system, right at the meeting point, we can have some current, and then the next electron is on the island, we are blocked again, and etc., etc., and this continues. This gives rise, now I was talking only about this axis, but we of course have also the source drain bias. So this is a very famous type of measurement when you work with quantum dots in electronic devices. They're called Coulomb diamonds. So what we have now is that we can continuously adjust this ladder with a gate, but we can also of course continuously adjust the source drain bias window across the structure. So on this axis we have the source drain bias window that grows positively or negatively, and here we have the gate voltage. And both ways we can map out a region where we have no current, no conductance from the structure, because we have a discrete number of charges on that, but then there is this degeneracy point here where you have the first, where you have the next chemical potential level coming in, you can have current. So basically the system here is in between the two charge states. And you can bridge this gap either through a gate voltage or through your bias window. So for example, in this case we have now two levels within our bias window. So this would correspond to one of these edges. Yeah. This measurement is known in the community as Coulomb diamonds, this structure. All right. How do we know that this is a classical system? Everything I showed you was just a metallic island. Okay, I showed the previous slide was a semiconductor measurement that I showed you, but really this is all classical physics. How do you know that from a picture like this?
They're not blurred in any way.
The reason, okay, this is of course a schematic, so there's no real blurriness happening. The answer is that these are all perfectly equal size, right? Like, of course they are because we drew it, but in reality, when you measure this on a metallic island, this will also be a perfectly constant size. Each diamond will have the same size. That tells you that there are no energy corrections happening, that all you have is this classical charging energy in the system. Okay? This is how it looks in the real semiconductor. It's an example from Mourik, from the team of Thomas Shapers. This is on a nanowire, so this is a quantum dot in a nanowire. And why can we call it a quantum dot? One of the reasons is that these diamonds vastly change their size. And that tells you that there is an additional energy scale involved in not only charging energy, but something else. And of course, that is a consequence here of confining the system enough so that we get an orbital state. So now we need to also consider orbital energies of an electron in a confined space. Okay? So this is, yeah, for an experimentalist, when you see that your diamonds have a changing size, it means that you have a changing orbital energy in a quantum dot. So once you start seeing that, it is a good indication your system is no longer a classical island, but it has become quantum. All right, so now let's think a little bit, given that we have this, given that we can make one of these small islands in a semiconductor, that we have control over the number of electrons in there. Then, of course, you can sort of map this onto the Vincent criteria, and that is what Danielus and David Vincenzo did in 1998. They sort of gave a blueprint to us as a community, how would a spin-based quantum computer look like. The idea is that you have individual quantum dots on which you define a qubit. Qubit is defined on the spin of the electron, single electron. For that you need to apply some magnetic field to define the spin state, lift the spin degeneracy. Then there is gates in between that can turn on and off coupling between the the spin qubits so that you can have conditional effects. Control goes via, of course, via spin resonance techniques. I will talk about that later. So we can apply microwave pulses to control the spins, and we all do that then in one of these two-dimensional structures. So this was sort of one of the earliest blueprints of a spin-based quantum computer. But funnily enough, this is at the very end. I will show an example where people have, after all these years, this is more than 25 years, people are sort of at the level of this schematic, maybe double the size of it. That is where the field is at. So, how does that work? How do we define our spin qubit? First of all, we need to have a single electron in the quantum dot, okay, or at least a single uniquely defined orbital state. The orbital state is spin degenerate, so we need to do something to lift the spin degeneracy, and that is, of course, the Zeeman effect. So for a normal spin 1/2 type system, we apply a magnetic field and we get the Zeeman energy out of it. Okay, then depending on all the various materials, you get an effective G factor here. For gallium arsenide, that happens to be minus 0.44. So this is a renormalization of the free space G factor that comes from the effective band structure approximation for these type of materials. We get an effective mass and we get an effective G factor out of that. Okay? So, and here we can now define, we have now a quantum mechanical two-level system and we can call it a qubit. We have spin up, which we call 0, spin down, which we call 1. And in principle, if we can somehow control this, we can have superpositions and we can have a qubit. Okay? But that's at the very basic level, the concept. Now, operation goes via electron spin resonance. So we apply a microwave pulse with a frequency that matches this energy difference. When we do that, we can flip the spin. So this allows us for control. And by doing that in a timed manner, by making it a pulse, not a continuous field, we can control how much we flip the spin, how much we rotate it. Then in terms of two-qubit operation, if we have two of these quantum dots next to each other, and we have an extra gate in between that can control how much these two wave functions overlap, that is what allows us to do two-qubit operation, conditional gate. Because the moment we lower this barrier and the wave functions overlap a little bit, we get coupling terms between the two qubits. By turning that on and off, etc., we can implement conditional gates. Yeah?
Could you tell a little bit more details how you control this microwave?
Yeah, it will come in a few more slides. I'm just giving you the overview now, and then I will fill this in a bit. Okay? So just be a bit more patient. Thank you. So this is just an example that it actually can be done, and this was, I think the first time, this probably was in 1995. This was on a vertical quantum dot, so it wasn't so useful for spin qubits. Later this had to be transferred to gallium arsenide. It's work from my former PhD supervisor in collaboration between Delft and Japan. And here you can really see that they went down to the very last electron, so no electron left in this quantum dot. First electron, second electron, you see this unequal size of the Coulomb diamonds, excited states visible, etc. And this is a,
So the color represents...
Sorry. So on this axis we have gate voltage sections. We have gate voltage on this axis towards drain bias voltage on this axis, and color in this case represents conductance, differential conductance. So where you see bright lines, you have a lot of conductance. Where it is white, there is no conductance. So these are regions of Coulomb blockade, and when we are at the edge of the Coulomb diamond, we have transport. And then, So this is just as an example that this was actually done. That this is a quantum object. You can also see it from the dispersion of the peaks as a function of magnetic field. So this is the position of one of these peaks here in magnetic field. And you can see that it is slowly shifting in magnetic field. There is a certain order to the energy differences. Overall it's going down, but sometimes it peaks, etc. this can all be interpreted if you start studying the theory of orbital states in quantum dots. So this was in the mid-90s, a big research topic, I would say. If you have a circular dot, for example, you can say something about the symmetries in the dot and the orbital states. You can map that to these various positions of these peaks, etc., and how they evolve in magnetic field. Okay? Then we can also look at Zeeman splitting in these quantum dots. So this is, I think, the first observation, but you can see that that is now done in gallium arsenide, so in a planar structure where we can actually make electronic devices out of it. So here is our quantum dot. People are monitoring the transport through the quantum dot, and here we plot conductance again. And what you can see is that this is the top of a diamond here. And what you can see is that this line here is slowly splitting. Okay, so you go from 6 Tesla to 10 Tesla to 14 Tesla, and this splitting here is growing. This you can fit to the effective G factor, and you find more or less the gallium arsenide G factor. Okay, so that is what is happening here. So this shows that Zeeman energy is there, it is measurable. Gallium arsenide, of course, has a very small G factor, so you need to apply really sizable magnetic fields to be able to see it. So, yeah, this tells you that you can make the system that you want to have to make a spin qubit out of it. All right, this is the, sorry, I should have shown this before, this is a diagram that belongs to it. Yeah, so at this point now here, you have only one of the two levels within your bias window, so you have some current, and then when you put it, the bias window a bit higher, you have both of them contributing, and that is why you get this extra step in this extra conductance line here. Okay, and here you are blockaded. Right? So this is a way you can in principle make a spin qubit. Now we need to be able to read this out, that we're actually doing it. Like this is all done time average DC transport, right? Like you see a static splitting. So for that, what we need two things. We need charge detection to work. So real time, as you go, charge detection, and you need to be able to convert spin to charge. Measuring spin, a single spin directly in experiment is very, very difficult. Measuring a single charge, as you could see from these measurements earlier, is possible. We can do that. So, how this was done first with any structure that has a nonlinear conductance as a function of the electrostatics around it can do the job. So traditionally this was done by making a QPC right next to a quantum dot. So on top of the two-dimensional electron gas, you not only make your dot, but you also make this type of constriction that allows you to make a quantum point contact. So yeah, that gives you quantized levels in this constriction, and I don't know if you need to go through this. Have you seen point contact? Yeah? Yeah. So then you know the concept. We have quantized conductance now, and the idea is, of course, that this is a highly nonlinear IV. In the ideal case, it is like 2 steps. In reality, it is, of course, smoother. Yeah, but as you sweep a gate and for the bias voltage, you can access more channels in the QPC. So what you do is you work somewhere on the steep slope. That is where you tune your QPC, and you have it sit right next to a dot. Now here, the charge on the quantum dot will actually affect where you sit on this curve. It is a little bit of additional, you can view it as an additional gate potential to the QPC. Okay, so the dot needs to be capacitively coupled to the QPC. If that is the case, then it means you are moving back and forth a little bit on this axis, which means if you sit on a steep section here, you can actually measure a change in current. And this is really quite sensitive to the level of single charges. All right, so this is how such a device now looks like. You have your quantum dot here, And next to it, right next to it, you have your QPC. So it is a bigger structure. It's a smoother wire construction. You pass current through it from here to here. It's tuned up to the point that you have a QPC. And you operate it over here. Okay? And now you look at differences in the differential conductance of the QPC. So you're going to keep monitoring either the current or the direct current or the differential conductance of the QPC. Now, this now depends on the fact how many electrons are present here. If there's more or less electrons sitting on the dot, it will affect the current through the QPC. So, here is the idea that whenever you are sitting in a well-defined spin state, okay, nothing will change over time. You have a fixed occupation of 1 in the dot. It's whatever. It could be an arbitrary number, but your occupation is fixed. So now, when we have something here that whatever we do, an operation, it could be a spin flip, or we play with a gate, so that first we sit below a reservoir, now we sit above it. The charge can tunnel out. We will have this step over time of the charge occupation of the dot. So in this particular example, we have a characteristic tunnel time of this barrier. So once we put an electron in, we put it above. Within a certain tunnel time, it will tunnel out. And then after another one of these tunnel times, it will tunnel back in. Yeah?
So the sensing is sensitive to the occupation of the dot, but not to the transition of the charge. So it's about the capacitance of the dot, or
So he said, yes. In this scheme, yes. But your question is a good one. It is also possible to sense changes in capacitance. So, but I would say for the purpose of what I want to present, we can think about static charge. So sensing a change in the static charge between two different situations through the capacitive coupling. It is definitely possible also to measure moving charge. So yeah, you monitor that. But it's a slightly different readout scheme. All right, so this is a typical scheme that you can that you can operate. So you have your dot defined. You start with an empty dot. You load a spin on it, either a spin of unknown species, spin up or spin down. Then you put your energy difference of those two spin states, so the Zeeman energy, you put half of that more or less above the reservoir height here. Okay? Now, depending on the spin species, the electron can either tunnel out or not. And then the next electron that tunnels in will likely be the ground state. So this is a way, and then you can empty it again. So if you now look at the pulses that you have here, so we start with an empty quantum dot, we inject an electron and we wait. Okay? If it is an excited state, it will slowly decay and we will end up in the ground state. Then we do a pulse to do the readout, so we need to put those two levels right in between here of the reservoir, and then at the end we empty the quantum dot. And this is the corresponding range you measure in current of the QPC. So first we have an increase in QPC current because we put one charge into the dot. Okay? Then that happens over here. So when we start over here, then we put it above, below the Fermi level of the reservoir. It takes should be a time scale of the order gamma of the tunneling time. Then the current drops a little bit because something changed in the electrostatic environment. And then we can have tunneling of either of the two species or not. Okay, so within the tunnel time gamma, we can have a tunneling event or not, depending on the spin species in here. And then we have a little bit of extra current until within tunnel time gamma again, you tunnel charge back in, and the current changed again to this previous value, and this is then your final pulse you apply to empty the dot. The point is that this space here tells you if you had spin up or spin down. Once you have the system characterized, you know through the value of current here if you had spin up or spin down that you loaded onto the electron, or the excited state spin down has decayed inside the dot to spin up. Okay. So this is what we call spin to charge conversion. And here you see the measurement. So this little blob here in the real measurement, it is this tiny blip here in the current. So this scale here, I think it is femtoamps or picoamps. I don't know, but it's a tiny, in any case, it's a tiny current, barely visible. It's at the edge of the detection limit of the instrumentation. Yeah, this was the first time that anybody was able to measure the tunneling of a single spin state out of a quantum dot. Okay, so it is really this sequence that I just showed you that was performed here. Fill the dot with an unknown electron species, and then do readout, and the readout blip tells you what you loaded onto the dot. Okay? Now, this wait time here, you can use that to estimate how long it takes for the electron to decay. If you measure very fast, the chances that any decay mechanism has kicked in is low, so you are providing a more true measurement of what you initially loaded. The longer you wait, the higher the chances the electron has relaxed to the ground state. Okay? And that is exactly what is measured here, so this is spin relaxation time. So this is decaying from the excited energy state to the ground state of the dot, and that is as a function of wait time before you perform the readout while the electron is sitting idle on the dot of an unknown but defined spin species, and that gives you a handle on what we call the T1 time. So this is the energy decay of the spin qubit. Okay, and that is quite long, it's in the millisecond range, and basically compared to the operation speeds, this was an important result at the time, telling you that this is good enough to move on to quantum computing, basically. This is, yep.
What about T2?
Yeah, we will get to that in a bit. Of course, T2, in gallium arsenide, T2 was absolutely horrible. It was like 10 nanoseconds or so, because of all the nuclear speeds. Yep.
So, during this without procedure, we shift the levels of the system.
Yeah.
Does it influence on the T1 and T2 time?
I think that in the end, once you have done the best you can in terms of material design, etc., make the system as quiet as possible from the perspective of a spin, what will limit you is the quality of your pulses, etc., how sharp these are, how ideal these are. That is what is going to, in the end, limit the performance of your spin qubit. I think that in these early generation experiments, it was probably not so important. But nowadays, pulse engineering, etc., is a big topic. To do this in the most optimal way to avoid effects on the performance of the qubit, yes. But, yeah, so principle, yes. Maybe we take a break, 5 minutes or so. Is that a good idea? Yeah, I think this is a good point. So we reconvene in 5 minutes.